Hi, thanks for tuning in, and I apologize for the last minute lecture cancel. A meeting came up and got rescheduled to our time slot, and so something I can't miss. So anyway, I'm going to cover the content I wanted to cover today, and I hope you guys watch this, and we'll continue on Wednesday. And just a friendly reminder that the classroom has been moved, so I will see you guys in Bunch Hall on Wednesday. Okay, so on Friday we left off and we talked about flow control, kind of the if statements, and so we will continue on in that. And so here we're going to talk about if and else statements. Okay, so we've got else statements. Which talk about what the program or what your script will do when the original if statement, if those conditions are not met, okay? And if you want to check for another condition, you can do that, and you can have an else if. So you check for an initial if, and if that condition is not met, then it will trigger the else statement, and then you can check for another conditional there. And it is important to note that the else, the lines on else are only triggered if the original if statement is false. If this if statement is true, then nothing here is triggered, nothing here is even evaluated. So you could have kind of an error or something, but nothing will happen if the original statement is true. So if this thing were true, then it would execute this and skip everything, these other else statements. Okay. An important thing is that you put else on the same line as the closing curly brace. Otherwise, R will see the closing curly brace and think that that the if statement is complete. Okay, so here's an example. X is equal to 3. We run some code here that just says if x is less than 0, that's not going to be true, so this is not executed. Then it goes to the next line and it says, well, that wasn't true, so let's see what happens here. We have an else if x is greater than 0, that is true, so it prints out positive. And because this statement was true, it will not even look at this one, and so this is not run or even evaluated. Over here we've got x equal to 0, and so here this is false, and so this is not run or evaluated. This is false, so this print positive is not run or evaluated, and so because both of these earlier if statements were false, it will run the last line here in this last else statement, print 0, and that's what it does. Okay. Here we've got some poorly written code. Okay, I've got x is equal to 3. It evaluates this. If x is greater than 0, print positive. That is true. Okay, so it prints positive, and then because this thing evaluated to true, it doesn't even bother checking this. So it's not going to even check to see x greater than 1, because the else is only evaluated or only checked when the original if statement is false. So in that case, it's not evaluated. So we don't see any of these results over here. Okay. Sometimes all you want to do is assign something to another value inside your if statement. So it's like if x is equal to 5, then n will take on the value yes. Otherwise, it takes on the value no. Okay, this is simple and easy to understand. You can also do the exact same code like this. Okay, so you have an if-else, which does this, which returns the value here, and you can assign it to n, whatever you've got here. Either way, if you don't remember this, this will work fine, just in your code. Okay, now we'll talk about loops. Okay, so probably the simplest and most common type of loop in R is the for loop, and you give it a vector, including lists or whatever it might be, and R simply iterates through all elements in that vector. Now, probably when you create loops, the most common vector that you'll give is a sequence of integers. So you do something like 1:10, and it will do the same action for the values 1 through 10 in that vector 1 through 10. But you're not limited to giving it a vector of integers. You can give it a list, you can give it a vector of characters, and it will just run whatever code is in there for each value in that vector, okay? And here we say x in 1 through 10, and so when you first run it, x will take on the first value in the vector, and it says just cat, so kind of concatenate 1 squared, so it puts that, outputs that to the screen. And then once it finishes what's inside the loop, then it goes back and it says, okay, now we're going to go to the next value in the vector. X is now 2, and we're going to do 2 squared. And we cat that, and we get 4. And then it says, okay, what's the next thing we're going to do? We're going to say x is 3, and it goes on, and it prints out the squares of 1 through 10. Here's an example where I've created a list. I've created a list L with the values 1 through 3, letters 1 through 7, and the values true and false. Let me just kind of create this just so you can kind of see the structure of L. So L, we can see, is a list of 3 objects, or three items, and it's a integer vector, character vector, and a logical vector. And here we're just saying print out the length of y. So it says for y in L. So it's the first time we run the code, y is going to be the integer vector 1 through 3, and it prints out the length of that, which is 3. Then we say, okay, now go to the next item in the list, which is going to be the character vector 1 through 7. And so y takes on that value, and we say print the length of y, and it's going to say it's 7. And then it says, you know, what's the length of the third thing? 2, okay? If I can just quickly modify this code, if instead of saying cat, if I said print type of y, then it will print out on the first line integer, then character, then logical. Okay, and that's what we have. So it's just going through each item in whatever vector you provide it. Okay, and again, lists themselves are viewed as vectors in R, and it just goes through each element there. Here we have the states, okay, state names 1 through 5. Okay, this is available in the library data sets. You can just say state.name. And so we got Alabama, Alaska, Arizona, Arkansas, California. And we can say for each item here, state and state name. So every time we run, it's going to take on a different value here. And we can say state has, so it takes on the value state has, and then we're going to do number of characters, 7 letters in it. Okay, if I just did length instead of n characters, it would be, you know, how long is the length of this first object? 1. How long is the length of the second object? 1. How long is the length of this object? 1. Okay, and then so the length would just be 1 for all of these. What we're asking for is number of characters, and California has 10 characters in it, and so that's what appears in this loop. In R, you'll often want to store the results of your calculations that you've done in a loop, okay? And so the best practice is to create an object where you will store the results and then and update the elements in that object rather than trying to grow the object. You can grow the object, and sometimes in a pinch you just want to write a quick piece of code and that's what you want to do. That's fine, but if your object is, if your loop is quite long, then doing that kind of operation could just not be very efficient. So anyway, here I'm just creating an empty vector, okay, and I'm repeating NA 10 times, okay? The reason why I want to do NA and not 0 is that if, for whatever reason, let's say I had a vector of 100, okay, for results, I repeated the value 0 100 times, and then I run the vector for 1 through 10, the first 10 items will be this, but then items 11 through 100 will be 0, okay? And then if I were to ask, what's the mean of that, you're going to have a whole bunch of zeros being factored into the mean, which is not what you want. If you have an NA, then you will have answers only for the first 10. Everything else will be NA. If you calculate the mean, it will return NA, but if you say remove the NAs, you'll get the mean of the values that you actually did. So I recommend using NAs. Anyway, so here I've got the for loop for x in the vector 1 through 10. We're going to square x, and we're going to store the result, this thing, x squared, into our results vector in slot x. So the first time we run it, it goes in the first slot. The second time we run it, it goes into the second slot, so on and so forth. I think you've probably seen something like this already, so this should look very familiar. Okay, these are what we would consider bad ways to store results of a vector. They work, okay? They work. They're not wrong, but they are a little bit clunkier, okay? So here I'm going to create just an empty vector here, okay? So this would just be, what is results here? This would be integer 0, right? I mean, not integer, logical 0, right? So if I say results, it's going to be empty vector, and I just say type, what is results? It says, oh, I'm sorry, it's null right now. Not logical 0, it's just an empty vector, okay? And then all we do is we're just concatenating the current results vector with the value x squared, and then and we grow. So the first time we run it, basically results is going to be concatenate our null with 1, and we get this, and then we're going to concatenate results, our current vector, with 4, and results grows, so on and so forth, and we do that every single time. This requires quite a bit of overhead in memory because we've got to create copies of the vector every single time. This is also not good. Here I start off with just a vector of 0, and then I replace each thing. This requires that R is resized every single time, which requires a little bit of extra processing power. Other than for loops, so for loops will run the code for every object in your vector, every item inside a vector. A while loop will keep running until a condition is no longer met. So it says while, and then you have a condition that the loop will do as long as this condition is true, and then it runs the code inside. So if you aren't sure how long something is going to run, okay, so with a for loop you can say I want this to do 500 iterations, and you would create a vector with a length of 500. With a while loop, you create a condition, and it will run until that condition is no longer met. So that might only be 5 iterations, it might be 5,000 iterations. And so while gives us that kind of flexibility, okay? And so here I'm saying I takes on the value 1, and we're going to create a results vector to store our results, and then we just say while I is less than or equal to 10, update the results vector I here, and then after you do that, increment I so that it takes on the next value, and so I will go up to 10, and then so it runs, and then once it gets to, so I equal to 10, it executes this. In the 10th slot in results, it puts in 100, then I becomes 11. It goes back to the top, and then says, is 11 less than or equal to 10? No, okay? And so the results is this. If I actually check the value of I at that point in time, I will take on the value of 11. So here I starts off 1. We will create our results vector. We run this, and now if we ask what are the results are the vector, and we ask what is I is now 11, and that's why the code stopped running. Okay, if you have a bad condition here, you could get stuck in an infinite loop. Okay, if this is always going to be true, if for whatever reason this thing is never going to be false, then the while loop will run forever. Okay, and if that happens while you're running code, so for example, if I just say while 1 is equal to 1 or something like this, so this is running forever, it's not stopping. Okay, I've got to click stop here. There's often a stop sign will appear here, or maybe a stop sign will appear inside your console, and you can stop the code that way. You don't have to turn off your computer or something like that. Okay, there's another loop called repeat, and a repeat will just repeat whatever's inside the loop forever until it runs into a break statement. Okay, so here I've done something similar. I is 1. We create a results vector. We're going to update the results vector with the value I squared, and we increment I. And then if I is greater than 10, then we will exit the loop. We write break. So break is what causes us to stop running the code inside a loop. So here we go, and again in this bit of code, when we run it, we get a results vector, and if we check the value of I, it takes on the value of 11 because it kept incrementing, and then so when I was 10, it updated results and put in 100. Then it updates 10I to 10 plus 1, 11. And then finally, it will say, well, if I, which is now 11, is greater than 10, that's true. This statement is now true, so it executes break, which causes it to kick out of the loop. So we've got a few keywords here. This is we saw break. Break ends the loop. If you're inside a loop, it breaks the innermost loop. And then next just says, okay, you know what? End the current iteration and go on to the next iteration here. So here I've got for I in 1 through 10, if I is divisible by 2, so I divided mod 2 equals 0. So if I is an even number, hit break. Okay. Otherwise, cat I. So it runs with I equal to 1. This is false, so it doesn't run this. And then it cats 1 to the screen. Then it goes back to the top of the loop. I is now 2. 2 divided by 2, or not 2 divided by 2, but 2 mod 2 is 0. So it executes break, and it stops. Okay. I'm going to have the exact same code, but instead of break, I've got next. Okay, so here we do this, and then so it runs it for 1, and it cats 1 to the screen. It goes to 2, and it starts the code for 2, but then as soon as it hits the next, it skips everything else. It skips the rest of the code, so this is not executed because as soon as it hits next, it goes, oh, I got to go to the next one. So it doesn't cat 2 to the screen, but it does it for 3, and it executes 3 on the it cats 3 to the screen, and so on. And so now we get all of the odd numbers printed out because every time an even number appeared, the next keyword was triggered. Okay, we have a few things. So back here I said earlier we created this list L, which had several things in it, and we said you could just have the loop run through each object in the list, okay? But sometimes you want the actual index, and it is useful to have it. So we have a few things such as sequence, sequence along, and sequence length. So here I've got x and sequence along L. This basically creates a vector 1, 2, and 3, okay? And so if we want the length of each thing here, I would do sequence along L. And the important thing to note here is that we now we just have the values 1, 2, 3, and so if I want the length of L, length of the thing in there, I've got to use the double square bracket to say I want the object inside L. If I use the single square bracket, then L would be subset to the first thing, but it would be the first train car. And so if we ask what's the length of L single bracket 1, it's going to say, well, that's one train car. There's something inside there, but the length of that one train car is 1. And so if we want the length of whatever's inside, we got to use the double square bracket. That's not the issue back here when we did when we created this loop, because here it goes into each train car, and y takes on the value of the object inside each train car. Okay, so that's what we have. Sequence along L. So so again, L is this, and if I do sequence along L, we have 1, 2, 3. Okay, and so L single bracket 1 is a list of length 1. L double bracket 1 is the vector 1, 2, 3. These are other ways of producing the same thing. You can just do 1 colon length of L, sequence along L, or sequence length of 3, and we all get the vector kind of 1, 2, 3. So there's a few ways to do this. You might see, depending on your coding preference, you might write any of these things. Okay, all of these things that we've done could have just been done using subsetting so far, but loops are often very handy to have. R is known to be not the most efficient loop programming language, but loops do work, and so so you can use them. If you can think of vectorized ways to do things, that could be good too. But if you can't, you can use a loop. Okay, now I'm going to talk about functions. So functions are very important, and they come in this form where to create a function, you have the name of the function, and you say it's going to be a function. You give it some arguments. These are all the values that go into the function. The function runs some code, some different expressions, and then at the end it will return some kind of output. So yeah, the names of the variables are supplied in the arguments, and then the final result is returned here. Okay. If the function has only one expression, you can leave off this curly brace immediately after function. So here we can say, I just want to return the value x times x, okay? And if we don't use the command return, it will just return the last expression in the function. So here we've left off the curly brace. There's only one line. It will also return the very last value here, okay? The value, the function f itself is an object in R, which means you can use them just like any other object. So you can throw a function inside a list, and if we ask, what's this list? It's going to say, well, in the first train car, you've got a function of x times x. If you ask what the type of is, R calls these things closures. Don't worry too much about that. Just know that when you see closure, it's a function, and R calls them closures when we ask for type of. Okay, functions can return any object, including other functions. So here I've created a function that returns this function. So I'm creating a function of x, the function of x returns this function of y. Okay, so here I'm going to say create a function where x is 1. Okay, and so that's going to create a function of y where x is 1. So it's going to when we do that, we'll have a function that does 1 plus y. So we call this the add 1 function. And so, so if I say f2 of 1 creates the add 1 function, we can say add 1 to 7, and we get back 8. Okay. Here, if looking at this first bit, f2 of 4 creates a function where x is equal to 4. So now this is basically the add 4 function to the value 1, and we get back 5. Okay, don't worry about this. You're not going to be tested on this idea of functions returning other functions, at least not in my class. But this is just kind of a neat little thing that R is capable of doing. And you can kind of play around with this concept, and there might be a time where something like this is useful, especially if you find yourself repeating certain commands and certain things. Okay. Yeah, I think I talked about this already. We have explicit returns where you use the command return. Okay, so here I've got function of x and return the value x times x. Okay, or it's implicit where you just say function of x, and then the very last line in the code is x times x, and so it returns the very last thing that was run. Okay, so this would be the explicit and the implicit. One thing to note is that when you're running a function, as soon as it hits return, okay, because the sole purpose of a function is to run code and return a value. And so if you've got code and you use this return, as soon as that return is executed, the rest of the code stops because the function has fulfilled its purpose in life of returning the value. And so it's not going to bother trying to continue doing anything else because a function can only return one value. So as soon as it's returned one value, it's done. Its purpose has been fulfilled. It no longer needs to continue running code. So that's just one thing to keep in mind. If you have a return in the function, after that return is executed, the other stuff is not going to be run at all. Okay, this is a very important concept. Functions can return only one object. Okay, so if there's like multiple things that you want returned, okay, so if you want to return more than one value, you have to group them into a single object using either a vector or a list. Okay, so you know, in R you might create some kind of linear model 1 through 9, and y is going to be okay, so you might create a model where you are creating the linear model between y and x or something like that. Okay, if you ask for the model, it looks like this, but if we actually ask for the structure of our model, what we see is that it's got a whole bunch of values that it returns, but it's actually just one object, a list of 12. Okay, so all the kind of the functions that are written in R, of which linear model LM is one of them, it returns only one object, many values. Okay, but it's a single list of 12. Okay, and so here if you want to return 3 values, x squared, and x cubed, you can group them together into a single vector, and it will do that for you. Okay, and here I'm, instead of returning a vector, I'm returning a named list where the names are x, the square, and the cube, and f of 2 returns back a single list of 3 train cars, and the values inside those train cars are 2, 4, and 8. Okay, and because each of these operations inside here are vectorized, like you can have provide it a vector and it will square, or provide a vector and it will cube it. We can also provide a vector of values for f. Okay, this would not work if one of these was an if statement. An if statement can only take in one value, so it would hang up there. But because each of these operations are vectorized, it works just fine. When we define a function, we're also implicitly defining names for the arguments, okay? So here I've created a function x, y, and z, which means every time we run these things inside, every time we need to refer to these values in the function, we got to call them by the names that we used in the argument. So we got to call them by x, y, and z, okay? And so here, I'm creating the output of this function is just create a character string where we've pasted x and the value of x, y and the value of y, and z and the value of z. And so we say, 1, 2, 3 is going to take on the values x, y, and z. And so when you call the function, it puts them in the order that they appear, 1, 2, and 3. You can also say I want z to be 1, x to be 2, and y to be 3, okay? And then, so notice z, x, and y are not in the order x, y, z, and r will match them accordingly. So you said, well, z is 1, so it does indeed put z into the z spot and the x and y into the correct spot. Okay. Here I've said y is 2, okay? So it's going to put y into the y spot, and then everything else it just tries to match up in the order that they appear. So 1 will go into x and 3 will go to z. And here I've said y is 2 and x is 3, and so it says, well, I've got to figure out where this 1 goes, and that's going to go into the spot z. Okay. Here I've got 1, 2, 3, and then m is equal to 1. Then it complains because it's saying you're giving me a value, an unused argument called m, and I don't know what to do with it. So it stops it. It doesn't. It's not a warning. It's an error, and it doesn't run the code. You can also give it default values. So when you define the function, so back here I just said we have a function of x, y, and z, and if I didn't provide one of these values, it would error out. It would say I don't have this. I don't have a value for x, y, or z. Okay. Here you can give it default values. You say x is 1, the default is 1, y, the default is 1, and z, the default is 1. Okay. Same function as before. So I say run f. And I didn't give it any values. It just uses the defaults. I say 2 goes into the x spot, everything else takes default. Or here I got f of z is equal to 3. 3 goes into the z spot, and everything else takes the default values. Okay, now I'm going to kind of introduce this topic of scoping, and we'll cover this a little bit more. We'll have a lecture dedicated to environments, but this is an important concept. It's also a tough concept, and so you might need to rewatch this portion of the video. Or my suggestion is to kind of play around with the code and just kind of see what happens. Okay, so R has generous scoping rules, which means that if you have a function and it can't find a certain value inside that function, it's going to search for the higher scope. So here in the global environment, I'm going to say y is equal to 1. F is a function of x. X takes the value x plus y. Okay, and right now, nothing has actually happened. Oops. We've just defined a few things. Let me kind of clear out my environment here. So here I've got y, here I've got f, okay? Y has the value 1, f is this, okay? And now I'm going to call f of 3. So what happens when I run f of 3 is that 3 goes in for x, so now it's going to do 3 plus y. And it says, well, what is the value of y? It doesn't find y, because when you run a function, it creates this own little environment, okay? It creates this own little spot. Inside here, x takes on the value of 3, and then it says, I want you to return the value x plus y. But we don't know what y is. And so what R does, it says, well, let me search, okay? And it searches the global environment and says, you know what, y is equal to 1. So now I'm going to return 3 plus 1, and it gives back 4. Okay, here it says we're going to create y is equal to 1 in the global environment, g is a function of x. Inside this function, inside the environment here, y takes on the value of 2, and we want to return the value x plus y. So here, I say g of 3, x is the value of 3, so it's going to do x plus y. So 3 plus y, it says y is 2, and it returns back 5. What happens to the y in the global environment? So here, I'll clear this out. Let's just take a look. So y takes on 1 in the global environment. I'm creating this function g. G has not been executed. Okay. If we ask what is g, g is just the code that we've written. And now I'm going to execute g of 3. Okay. G of 3 returns back 5. Okay. And notice the y in the global environment remains 1. Okay. Because even though I assigned the value 2 to y and I executed this code, the value of 2 going to y exists only inside the environment for g. It doesn't touch the y inside the global environment. So here, we give x the value of 3, 3 plus y. Y is 2 inside the global environment, it returns back 5. And y is 2 inside the function environment for g, so it returns back 5. Y in the global environment remains 1. Okay, so this is important to note. Variables defined within a scope exist in that scope, so inside the function only, and only for the duration of that scope. So, any variables that you create inside the function exist only inside that function, and they don't interact with anything outside. Okay, so if variables exist with the same name outside the scope, which is what we saw with the y's, those are separate and do not interact with the variables inside the scope, nor are they overwritten. Okay, you can think of a function as its own separate environment that only communicates to the outside world via the arguments and the output expression, or the returned value. So inside, you're creating kind of this little bubble. The only way the stuff inside the bubble communicates to the outside world is through the arguments coming in, and then the output, the return value coming out. Everything else exists inside that bubble only for the duration of the scope, only while that function is run. As soon as the function is finished running, everything in that bubble disappears. Okay, whatever happened in there happened inside the bubble, and unless it's been recorded in the return value coming out, nobody has any idea what happened inside that bubble. Okay, so if you execute the command rm list equals ls, which removes everything inside the scope, okay, which you would not do, which is a terrible idea anyway, but that would just delete whatever is inside the function, inside the bubble. So you've created the function, and the function is running, you've got this bubble. If you do rm equals, remove everything in there, rm list equals ls, it's going to remove everything in the bubble. Everything outside of the world, nothing is affected, okay? The exception is the superassignment operator, the double arrow here. And that one is the way for us to interact from stuff inside to the outside. And I really hesitate to teach you this because some students see this as kind of a shortcut. The best practice is only to interact with stuff inside the environment through the arguments and the return value, okay? But I will show you a few examples of this, and I'm a little hesitant to do so just because it can create unexpected behavior. But it does exist, and there are certain cases where you want to use something like this, but I'd say these cases are rare. We'll talk about those when we cover reference class objects, which will come in several lectures, but I'll show you this. Okay. So here, these slides are all important. Make sure you understand what's happening with the scope stuff. Inside the global environment, we're creating the values x, y, and z, and they all take the value 1. I'm creating a function, f, where y takes on the value 2, okay? this creates y inside this function only. And so it doesn't interact here. We're inside the function f, we're creating a function g, okay? And again, so this creates a scope inside a scope. So you've got your bubble, and inside that bubble, you've got another bubble for g, okay? And inside that, z takes on the value 3. And we're asking, return the value x, y, and z. G was going to return this, and then f is going to return whatever g returns. So we ask, run f, okay? So we run f, y takes on 2, okay? And then it says, return g, okay? So now we say, okay, well, what is g? Okay, it's going to run the g that's defined in here. Okay, if I had another function out here called g, it's not going to run that one. It's going to run the g that's defined inside this bubble. Okay, and so so it says, okay, well, inside g, we're going to return the values x, y, and z. Z takes on the value 3. I also need a value x and y. Okay, well, we're starting on the innermost bubble. It says, well, I don't have y, search. Okay, we go to the next bubble out. It says, y is 2. Okay, so now I've got, we got to return the value x plus y is 2, z is 3. That's inside this bubble. We need a value x. We couldn't find it in the outer bubble for f. So it goes to the global environment and it finds x is 1. So now it says, okay, I've got 1, I've got 2, I've got 3. We're going to return the value 6. If we asked what is the values of x, y, and z, now we're in the global environment out here. Those two bubbles that we created, the bubble and the bubble inside, those are now gone, okay? And the values out here, x, y, and z, take on the values 1, 1, and 1. They are not affected by whatever happened inside here. Okay, again, we're going to, in the global environment, we're creating x, y, and z to be 1 out here. Now I'm creating a function f with a bubble, okay? And then inside of f, we've got g, another bubble, okay? However, inside f, I've got y superassignment 2, okay? So we're inside the bubble f, inside the scope for f. It says, take this value 2 and assign it in the global environment. So now we're actually going outside of the bubble, and we're changing the value y in the global environment. Inside there, we create another scope, g, okay, and inside there it says change the value of 3 in z, okay? Yeah, change the value of z to 3, okay? And so what it does is it's going to say, okay, well, I need to search the higher scope. So first it goes to the scope for f. It doesn't find a value z there. And it says, well, I got to assign this value 3. So it goes to the global environment and says, oh, here's z. I'm going to change the value z to 3. Then it says return x, y, and z. So again, it's starting inside the innermost scope. It says I need a values for x, y, and z. It doesn't find any values for x, y, and z here. It goes to the next scope. It's looking for x, y, and z. X, y, and z don't exist there either. And so it goes to the global environment. It finds the values 1, 2, and 3, and it returns that, and it gives us 6. If we ask what is the value of x, y, and z, these superassignment commands have changed the values in the global environment, and so those values are now 1, 2, and 3 in the global environment. Here I've got, oh, excuse me. Sorry, let me just go back. Okay, so we've got, in the global environment, we're creating x, y, and z, and so those are taking on the values 1 in the global environment. Okay, now I've got the function f. So when we execute this, this bubble is created, this scope. Inside that scope, we're creating the value y is 2. We also have this command y superassignment 4. Okay, so inside the scope of f, there's going to exist a value y, which has the value 2. Y superassignment 4 says, you know what, go to the global environment and change the value there of y to the value 4. Inside the scope of f, we're creating another environment, another function called g, and that exists there. Here, we say search the higher environment and assign the value 3 to z. Okay, so when we run that, what's going to happen is it says, okay, well, I couldn't find it's going to say, well, I'm not even going to bother searching inside this scope. We're going to go to the scope for f. It says I can't find a value z here, so I'm going to go higher, and it finds z in the global environment. And it changes that. Okay, and so when we ask to run f, what it's going to do is it's going to look for x, y, and z. Okay, starting on the innermost scope, because it's got to return, it says return the value that g, and so here it's returning x, y, and z. It says, okay, well, I couldn't find x in here. It goes here, and it says I can't find x in the f. It goes to the global environment, x is the value 1. Okay, now it says, okay, we're going to go here. We want to search for y. Can't find y here. It goes to f, and it says, oh, you know what? I've got an object y here, which has the value 2. So it takes that value 2. Then it says z. Okay, no z here, no z here. There's a z out here. Okay, z has the value of 3. So it's going to return the value of 1 plus 2 plus 3, and it gives us 6. However, if we go, and then once it's done executing, all those bubbles, those scopes disappear. And now we ask, in the global environment, what is the value of x, y, and z? X is 1, y is 4, because we changed the value 4 in the global environment here. Y is 4 and z is 3. Okay. Something similar, I've got y is 2 and z is 10 inside the function for f. Okay. And y is 4, and then here it asks us to do this. Okay, so let's execute this. Okay, and so here we get okay. And okay, so here we're creating x, y, and z with the value of 1 in the global environment. Inside the function f, we have the values y and z. Okay, y takes on the value 2 and z takes on the value 10. And then we say change the value of y to 4 in the higher up scope. So inside f, y is 2 and z is 10. This value of 4 gets written to the global environment. Okay. Inside the function g, it says change the value of z to 3. Okay. And so that exists in here. So when we execute this code g, it's going to say, okay, we're going to change the value of z to 3. So it goes up to this scope of inside f, and it says, you know what? I see a value z. Z is taken 10. I'm going to change that value to 3. Okay, and so we ask, when it returns x, y, and z, it's going to say, okay, I searched the higher scope, I found z is 3. I searched the higher scope, I found y is 2 inside this bubble. And then I can't find x anywhere, so I go to the global environment and I take on 1 for x. So x is 1, y is 2, and z has been reassigned to 3 here. Okay, but because z has been reassigned here, this z up here is spared. So anyway, it returns 6, and then we ask, what are the values in the global environment? The values are 1, y is 4, and z is 1, because this assignment of changing of z to 3 affects only the z inside this scope, because g exists inside of f. Okay, I hope that kind of makes sense, and go ahead and play around with this, see what happens if you change certain things and where these things exist and whatnot. This concept of scoping and environments we will cover in a little bit more detail in the coming lectures. Okay, and then so just in general, when we're talking about functions, the goal of functions is to have a piece of reusable code that we can use in other cases. So sometimes if you find yourself copying and pasting something, kind of the rule of thumb is, if you copy and paste the same bit of code twice, that's okay. If you if you have to copy and paste the code maybe your third time or fourth time, this is when you want to start writing a function. Okay, so you got one thing, you copy and paste it, and you got to just run the same thing and make a few changes. That's fine. 2 times is kind of the recommended limit. More than that, you want to start thinking about, maybe I need to create a function for this. And so that's what we want to do. Your functions should be we're hoping simple in nature, so that it makes sense when you look at your code later. And then again, keep in mind, you generally want to avoid using the super assignment, and you only want to have your function interact via the arguments coming in and the returned output going out. And everything else, treat that as a bubble that exists only inside the function, that disappear when the function is ended. Anyway, thanks for tuning in for today's lecture. Sorry I had to kind of last minute cancel the lecture, and I'll see you guys on Wednesday.